have the rate of change of P of t, so that would be dp dt, is directly proportional to P of t. So directly, so we have our K times P, directly proportional to P, and we want to find the equation for that. The long way to do that, separate, integrate, and go from there. The shortcut is, this looks just like this format. dy dx is equal to ky, which we know is going to become an exponential growth or decay problem. How do I know that? We have this dy, and this is ky. Same over here, we have the dp, and it's k times p. So we can quickly, without having to really do calculus, jump straight to p is equal to some new constant, e to the k, and I'm going to use t instead of x. Again, that is memorized. That is a shortcut. You do want to be careful. There are ones that look like the shortcut but aren't. For example, dp dt kx, not a shortcut. Dp dt equals k, I don't know, anything around the p, not a shortcut. It has to be dp dt equals kp, basically in this format, in order for it to equal that equation. So I did just want to take some time to re-emphasize that. The other example that I wanted to do, I wanted to do the loudness example. So for the first page was supposed to have the problem on it, but I realized somehow it got deleted when I shared it. It is on that page 2 of loudness, and I'm just going to copy it over, and then we can talk about it. If it will let me, there it goes. And so when we're looking at these problems, the main things that we're looking at is first matching it to the slope field. So it says y of x represents the loudness of sound measured in decibels, and x is representing the distance, and it is in meters. We have this initial condition. It says at a distance of 4, the loudness is 70. At a distance of 8, the loudness is 64. Looking at this, I can see that this should be a decreasing function. So I can eliminate not C and D. I can eliminate A and B. And then I just want to figure out which one is the best match. I did put a note on here. Imagine the y-axis is scaled by 10 for the loudness problem. So 4, 7 is going to be representing the 70. And 8, halfway between the 6 and the 7 will be close to the 64. So finding out which one matches best. Following the slope field of C, really steep. Slope field of D, much more gradual. So D is definitely the best choice for that problem. So let's go ahead and do the calculus part now. At this page. So again, we're going to go through the same basic steps from yesterday, just more practice, more of the same. Things that you, again, always want to pay attention to. The variables and the words attached to those variables. So we have y is going with the loudness, and we see that x is going with the distance. Look for the equation that gives us our differential equation. Y changes at a rate that is inversely proportional to x. And then let's go from there. So looking at this problem, y changes at a rate. So that's going to be dy dx. That is inversely proportional to x. So I have my k. Inversely is going to put it in the denominator. So we have k over x. So now I want to look at this. Is this a shortcut? Unfortunately, no, it's not k times y. It's k over x. So we are going to have to go about it the long way. Going about it the long way, we want to separate the variables. So I have dy is equal to k over x dx. not really a y that we need to deal with. Take the integral of both sides. There's a 1 right here technically. So we have 1 is equal to, k is a coefficient, x is in the denominator raised to the first power, so times the natural log of the absolute value of x plus c. One of the most common mistakes I see in these problems is when people take the integral, they leave off their plus c. If this is the AP exam and you leave off the plus c, that's where the AP grader stops grading your paper and they just go to the next problem. So that plus c is hugely important. This one's kind of nice because y is already solved for. So now we can go ahead and start using those initial conditions. So it says at a distance of 4, the loudness was 70. And at a distance of 8, the loudness was 64. So let's go ahead and plug it in. So y is 70. K times the natural log of 4. Absolute value of 4 is 4, so that's when I can drop it, plus c. Unfortunately, like the one yesterday, we had an initial condition at 0, so things canceled out. Nothing's canceling out right here. Same thing for the other one. 64 is equal to k times the natural log of 8 plus c. Looking at this, nothing canceled. We still have 2 unknowns, and we have 2 variables. So we need to reach back and think about some of those good algebra skills we've developed. How are we going to solve this? We basically have a systems of equations. How do we solve systems of equations in math? Some of you are stressed when you see that. We have substitution, we have graphing, we have the elimination method. If you're feeling fancy and remember pre-calc, we have matrices. There's lots of different ways that we can solve a system of equations of more than one variable. I'm going to go ahead and tell you the easiest one to use. For differential equation problems, elimination is always going to be the easiest method. Why is it going to be the easiest method? Elimination, remember, is when you're adding or subtracting 2 separate equations to create a new one. Since both of these always will have a plus c in them, you can always count on that variable canceling out. So I'm going to go ahead and subtract this bottom one from the top one. Again, we're just doing some algebra, fancy algebra 1. 70 minus 64 is 6. I have k natural log of 4 minus k natural log of 8. And as expected, the plus c's, c minus c, those cancel out. So remind ourselves what we're doing. We're trying to solve for k. So I have 6 is equal to, let's factor out that k to get it by itself. And then I could divide by that natural log of 4 minus the natural log of 8. I'm going to simplify it because it's ugly enough. Remember, when you're subtracting 2 logarithms, you can combine them together as a quotient. So what is k? I'm going to divide by the natural log of 1/2. K would be 6 over the natural log of 1/2. Not the prettiest looking k, but that is the k that we have to work with. So now we need to find the c. How do we find the c? We want to plug it back into an equation. Does it matter which one we choose? No. I'm just going to go ahead and choose that top one just because for me 70 looks a little bit easier to deal with than 64. So I have 70 is equal to, there's my k that I found. And that was times the natural log of 4 plus c. Still not a pretty looking answer, but we can write it out. What is c? C is equal to 70 minus, and I can subtract that expression. So then finishing out this problem, even though it doesn't look done, we are technically done. I can use the general solution, the k I found, and the c I found to write the particular solution. So I have y is equal to k times the natural log of x plus c. And you can leave your answer like this. I will say this does simplify way, way down. But on a free response question, that answer is perfectly okay. That would be the equation modeling the decibels away from the source of sound. Questions on that problem? Again, looking at it, there are some things I want to kind of point out to you. The calculus stopped there. Those three simple lines, that was the calculus. Everything over here, we did it by elimination, that is just algebra. Now, is it necessarily easy algebra? No, but we are kind of just doing some basic skills. We are doing elimination and then kind of simplifying it from there. Yes, Marcus, you have your hand up.
Yeah, for the final answer, does it matter if you leave the absolute value on the x?
If you dropped it, it would be fine, because it's kind of implying you're like x meters from the source. So if you just put the natural log of x, that would be fine.
Okay.
And again, there are ways you can simplify this way, way down, but we're just going to leave it like that for now. But yes, if you did drop the absolute value, it would be fine. So then we have some follow-up questions. Again, I'm not going to like insult your intelligence and like work these all out completely. Mainly with these follow-up questions are like, hey, are you smart enough to plug in a number and plug it in the right spot? For example, when I see what is the loudness when you're 10 meters away, I think most of you know, okay, so we have that y equation. And we just need to plug in 10 for the x, since that is what x is representing. Similar to the second one, again, it's a little bit uglier problem for me to actually work this one out, but at what distance, you're still using that y equals problem, but this time you're going to plug in 50 for y, and then you would solve for x. So I'm not going to work those out, but again, the calculus on these problems ends by like step 2 or 3. And then the remainder of the problem really is just like, do you know where to plug in numbers? Do you know how to solve equations? And things like that. So we're going to do one more example, and then that's where I'm going to stop at for today. And I want to do, which one do I like better? We'll do the balloon one. So we have a large balloon is being inflated. You could probably just stop there and eliminate some of your choices. This balloon is being inflated. It's getting bigger. The value of y is representing the diameter. The x is representing the time as this balloon's being inflated. We do have some initial conditions. After 1 minute, the diameter is 2. After 8 minutes, the diameter is 4. Knew it was already increasing. Now we just want to find the one that's the best match. Looking at B, can kind of see that that's a pretty steep one. You miss the 2 initial conditions. The one at A, much more gradual. It makes a lot more sense. Don't overcomplicate working with the slope field. What's more important, and what I think takes more practice, is actually writing the equation to figure out, can we write an equation to model this balloon being inflated? And try that one. Again, this is where we're going to stop at today. Again, for these problems, things that I definitely will keep emphasizing. When you see your variable, pay attention to what it represents. So the value of y is representing the diameter. So I'm also going to go ahead and highlight this other diameter I see later in the problem. And then it tells us that x is representing the time. And then we'll always have one statement that gives us the differential equation. Y changes at a rate inversely proportional to the square of the diameter. So let's go ahead and write that equation. Y changes at a rate, so we have dy dx inversely proportional. So we have our k, and everything's going to end up underneath it. What is it inversely proportional to? The square of the diameter. Which one's the diameter? The diameter is y. Looking at this, Unfortunately, it's not one of the special cases. It's not ky, it's k over y squared. So we are going to have to go through the calculus of separating, taking the integral, and going from there. Let's go ahead and separate the variables. I'm going to multiply by y squared, and then multiply by dx. Basically, we're cross multiplying. I've separated my variables. Again, I like keeping the k on the side with the x's. Let's take the integral. 1/3 y cubed is equal to k is a number, kx plus c. Could rewrite this one and solve it for y, but I know that I'm going to solve for k and c anyways, so I'm just going to leave it like that. So now let's go ahead and look at my initial conditions. After 1 minute, the diameter is 2. After 8 minutes, the diameter is 4. Let's plug those in. So I have 1/3 of 2 cubed is equal to k times 1 plus c. And then for the other one, I have 1/3 of 4 cubed, making sure you plug in the y for the y, is equal to k times 8 plus c. Unfortunately, again, we didn't have anything that was 0, so nothing canceled out, so we didn't get one of our variables easily. So we are going to have to solve this, and again, I do recommend solving this by elimination. It is going to be the easiest way to do a problem like this. I am going to clean it up before I do elimination. So 1/3 of 2 cubed, that's just 8/3 is equal to k plus c. If you don't like elimination, you can also do substitution. You'll get the same answer. 4 cubed is 64, and 1/3 of that is equal to 8k plus c. Again, elimination or substitution. I'm going to subtract one from the other. So I have 8 minus 64, negative 56, and that was in thirds. 1k minus 8k is negative 7k. And then, as expected, the c's subtract out. When you divide both sides by -7, it becomes positive. 56 divided by 7 is 8, and we still have the thirds there. So we get k is equal to 8/3. Once you know your k, you want to solve for c. Again, it doesn't matter which one you choose. I'm going to choose the top one because it's definitely the more simple of the two equations. So I have 8/3 is equal to plus c. So this one's pretty nice. The c value does happen to be 0. So combining that information, I can use that to write the particular solution. 1/3 of y cubed is equal to k x plus c. Could have left off that plus 0 if I wanted to. This is the equation showing the relationship between the diameter and time. If you want to solve it for y, which is often useful, we get y is equal to the cubed root of 8x. And again, think about how that can be used. I might say like, hey, what's the diameter at 10 minutes? Plug in 10 for x. When is the diameter going to be equal to 10? Plug in 10 for y, then solve it for x. So again, that will be how we use that equation. The calculus pretty much ended here. And all the rest after that really and truly was just algebra. Elimination, again, kind of hitting the highlights. That is my preferred way of solving systems. You can do substitution if that's what you're comfortable for. Maybe solve for k, plug it into the other equation. But I like elimination because you know that when you subtract one from the other, the c's are always going to cancel out. So it's always going to work out fairly nicely. Any questions on that problem? All right, so that's where I'm going to go ahead and end today's notes because I know these periods are short and I'd rather you have time to practice. That's really where you're truly going to learn a lot of this stuff. Your assignment that I want you working on, continue working through all of your homework. I will hang back once I kind of wrap up class if you have any questions on homework that you want to ask. But you have 4 homework assignments at this point, 1, 2, 3, and 4. 4 is honest and truly probably the best one in getting ready for your test. I used homework 4, looked at homework 4 as I was writing your test. Other things you can be working on. Your test is, again, I'm still planning on doing it for Friday. Other things you can complete is your briefcase binder. I do say all parts, but there was no quiz this unit, so don't need to worry about quiz corrections. And then, of course, we'll get to the optional practice when we get there. Tomorrow is still going to be a URL day. I plan on it mostly being a work day. I am still going to have like a warm up, but I do want to save most of the time for you to just work and practice. And then Thursday, when we're back on a regular schedule, is going to mostly be a work day as well. And then Friday, we're going to shoot to have our test. And then after that, starting next week, we'll be reviewing for the AP exam, especially since most of you are taking it that first administration on May the 4th. So at this point, like if you're good to go, then I will see you tomorrow. If you wanted to hang back and ask any questions about today's notes or any of the homework, then please do that, because I'd rather get your questions answered now instead of you just still having those questions kind of lingering. But I will see you all tomorrow unless you're staying behind to ask a few questions.
Bye. Thank you, Mr. Brown.
See you, Mitchell.
Mr. Brown, can I ask a question from homework 3?
Mm-hmm.
Thanks. It's the last one, number 40.
Number 40.
Yeah. I integrated it already, but I didn't know what initial to use so that I could solve it.
You're basically using, so calf weighs W sub 0 pounds at birth. So you're basically saying at 0, it weighs that. So it's not going to be an actual number you have to plug in.
So it'll just be like a equation?
Yeah.
Or expression?
An expression, basically, yeah.
Okay. So that's the only initial that you have? You're not?
Yeah. Yeah, because that's yeah, that's all they give you.
Okay. So you're just simplifying it, basically.
Yeah, I mean, do you want me to work? I can work it out.
Yes.
Because this is basically what you got when you separated it. So there's no K because they gave you the differential equation. I think that's important to notice.
Okay.
That's why you only need to have one initial condition.
Okay. Got
So
it.
when you go to integrate both sides, you do want to make sure you remember u sub, because that u would be the denominator and u prime would be -1. So when you integrate, it will be negative the natural log.
Natural log. Okay. Yeah.
But you do want to make sure that negative is there. And then that's just a 1, so you have t plus c. And then 2 choices. You can either try to get w by itself here or plug in your initial condition at this point. And it's kind of up to you. So like if you wanted to, I think it's easier to plug in the w now. So it says, hey, at birth, it weighs that amount, and that occurs at 0. So basically that's your c value. So plugging it in, we have this is equal to t, and then your c value is this.
Got it. Got it. Okay.
And then kind of, base e both sides and go from there.
Okay. And then on homework 2,
Mm-hmm.
number 22, I think. Where did it go?
Mm-hmm.
I got to the point where I was supposed to be integrating, but I think the other like variables kind of messed me up because like I have the integral of e to the negative r equals the integral of e to the negative 2s, and I just couldn't figure out how I was supposed to be integrating.
Yeah, so when I separate that, I would use like properties of exponents, right?
Yeah, I got that.
And then, so you end up having like 1 over e to the r dr, because you want the r's, you're treating the r's like the y kind of, and 1 over
Okay.
e to the 2s ds. So if it helps, you can just say turn the y's and turn the s's into x's, if that helps. Because really what you're integrating is e to the negative r dr is equal to e to the negative 2s ds. And then you have your u sub. And that would be a bit not simplified, but that would be your antiderivative.
Okay. Okay, I got it. It was late. Okay.
You're good.
Don't judge me. Okay. Thank you. Sorry, Mr. Brown.
You're good.
Okay. Thank you. That's all I needed.
See ya.
Bye, Mr. Brown.
Bye.
Mr. Brown,
Hey, Caroline.
so when I opened my OneNote for class,
Mm-hmm.
everything like deleted. So I went online and
Mm-hmm.
like everything was still there. But
Um,
slowly, like everything, like slowly a couple of like the things have been like re-uploading, but like still all of like my unit stuff isn't showing up.
so here's yours on my end, and it's there.
Like I can do it on like online, but then when I try to like
So
open in desktop,
I would recommend you might just have to re-download it all. So to do that, I would like click on the notebook for my class,
mm-hmm.
right click on it, and you're gonna click close this notebook, which is gonna remove it completely from your desktop app.
All right.
And then once you do that, to get it back, open it through Teams.
Open it through Teams
Go
or
to Teams. Yeah, I would recommend going through Teams.
Okay.
And I'll just share my screen. And when you go into Teams, like clearly click on my class. This is 5th period, but we'll do it. And click on like the class notebook tab. And then you're going to, once it loads, and this is basically just like reconnecting your desktop app to the OneNote. Do this little drop down and do open it in desktop app.
All right.
And it's going to take like 5,000 years because it's going to have to re-download everything from August. But it should also, like, it basically fixes any syncing issues with whatever it sometimes does.
Okay. All right. Thank you.
You're welcome.
All right.
See ya. Bye.